All right, this is the first lecture for Chapter 3, the problem portion. Starting off, you've looked at all the stuff up in top here on your own. But for the first problem, we're doing some equation writing. First one, write balanced chemical equations to correspond to each of the following descriptions. You have some solid calcium carbide, and it's going to react with water to form an aqueous solution of calcium hydroxide and some acetylene gas. That's a pretty powerful reaction. The acetylene gas, if you spark it, it makes a pretty substantial little explosion. It's a good time. I used to do a demo with that once upon a time. Anyways, all right, so starting off, you have calcium carbide, and you are adding to that some water. And it's telling us what the reaction is. It forms aqueous solution of calcium hydroxide. And this is one of the things you just have to, again, put along with some of the things we learned in Chapter 2. Calcium hydroxide, calcium is 2 plus. That 2 comes down here. Hydroxide is -1. Don't do anything with that. And it tells us very specifically what acetylene gas is right here. We have to go through and balance this out. And looking at all the elements, I always try to avoid hydrogen and oxygen until I'm done because they're everywhere. So hydrogen's here, here, and here. And oxygen is really only in a couple of spots, but we're going to hold off on that. First thing I'd like to take a look at here is the carbon. Carbon is found 2 here and 2 here. Okay, well, that didn't help at all. It's done. Calcium, I have 1 here and 1 here, and that's done. I guess let's take a look at the oxygens. I've got 2 oxygens and I've got 1 oxygen, so that hopefully is an easy fix. So the oxygens are balanced. The only things that aren't are the hydrogens, and let's just hope this works. I have 2 times 2, 4 hydrogens, 2 hydrogens plus 2 hydrogens, done. So that problem is taken care of, no worries. All right, let's take a look at B. For this one, we have when solid potassium chlorate is heated, it decomposes to form solid potassium chloride and oxygen gas. Okay. Solid potassium chlorate. Potassium chlorate is this. So chlorate is the one with the 3, 1 minus, and those guys balance out just as we see. And it decomposes to form solid potassium chloride, and potassium chloride is simply this. 1 potassium, 1 chloride, they're both 1s, they cancel each other out, no big deal. And oxygen gas. So oxygen gas is O2, and now we got to make sure everything is balanced out. Okay, 2 and 3. Those don't divide into each other really well, but I have to find the at least common multiple of the 2 of them, which is 6. So let's see if this works out. If I multiply a 3 in the front, I get 6. If I put a 2 in front, I get 6. But now I messed up my chlorides. I have 2. I need to put a 2 here, which also affects potassium, which is equally affected over here. Done. All right, last one on here for C is solid zinc metal reacts with sulfuric acid to form hydrogen as aqueous solution of zinc sulfate. Okay, let's go ahead and just run through that one really quick. Solid zinc. Got it. Reacts with sulfuric acid. This is not one of those common things you need to memorize. Sulfuric acid is H2SO4. Very common industrial acid. And it's going to form hydrogen gas. Okay. That's one of them Hofprinkels. So it's H2 diatomic and an aqueous solution of zinc sulfate. Zinc is always 2 plus, and sulfate is SO4 2 minus. And normally I would do that whole 2 in the brackets, but sulfate is 2 minus, zinc is 2 plus. They cancel each other out. Now the last part is to make sure that these guys are all balanced together. Sulfate is like a whole, and I can see that they're kind of the same. So those guys are good. Zinc is 1, zinc is 1, hydrogen is 2, hydrogen is 2. It just happens to work out. Good, nice and easy. All right, this last one is kind of a fun, weird problem. It's looking at the amount of oxygen, the percent by mass of oxygen in these compounds. So if you're ever curious about how much oxygen's in morphine, cocaine, codeine, or tetracycline, here was your chance to kind of do a problem like that. I know this is one of the things you've probably always been curious about, and here we go. All right, so it really all what this comes down to is what is the amount or mass percentage of oxygen in all of these compounds. So the way you have to do it is figure out the part of the whole. And we need to figure out what the whole mass is and then just deal with the oxygen portion. So the way I would look at this, and I didn't leave you a lot of room here, at least on my copy, figure out how much for each of these guys. So carbon happens to be 17, right there, 17 of them times a mass of 12 off the periodic table. And for the most part, close is close enough. That gives us 204 atomic mass units. Hydrogen, I have 19 of them times a mass of about 1. 19. Nitrogen, I have 1. The mass is about 14. And oxygen, I have 3 of them times mass of about 16, giving me 48. If I add that whole thing up, let's just deal with the oxygen first really quick. The mass of specifically what I'm looking for is oxygen. The mass of the whole thing here, if I add it up, is 285. Therefore, the part of the whole as a percentage is 16.8%. All right, you will do the same process for the other 3. And I'm not going to go through this whole part here. You will do that the same because the process will be exactly the same. The only thing really is going to differ is the amounts of each of these on there. But what I will tell you, if you do the whole process for all 3 of these, you should get a mass of 64 for the oxygen based out of the whole mass for the compound, 303, which would give you a percentage of 21.1%. And if we do the one for codeine, which is actually B, did a little out of order, you would get a mass of 48 out of 299, giving you a percentage of, if I can read my own writing, 16.1%. And the last one, tetracycline, the amount of oxygen in that compound is going to be 128, so 8 times 16, divided by the total mass of the compound. It's going to be 444. Hopefully you got that. And the mass would be 28.8% for the whole thing. Okay, let's look at 33. And I'll get started in this. I'll do one of them, and then we'll break it up and we'll move on to a whole nother video for this. So looking at this one here for 33, calculate the following quantities. So I want the mass in grams given the number of moles of sucrose. So this is a conversion using a little dimensional analysis. I have moles, 0.105. And I'm trying to get to grams. And the way I would process through that is, okay, so this happens to be moles of sucrose. This is the substance. and I will times in a line. I will put moles on the bottom. I started with moles. That's kind of like on top. So I put that on the bottom, and I want grams. If I do the whole math process like I did in the previous problem, 12 carbons times a mass of 12, 22 hydrogens times a mass of 1, 11 oxygens times a mass of 16 each, that'll add up to 342 grams about for every 1 mole. And if we do the math process, 0.105 moles times that many grams for every 1 mole, you should end up with 35.9 grams of sucrose. Okay, this is a good place to take a break, and we'll pick it up on part B next.